In this video, we will talk about how the concept of the atom was developed in antiquity and then re-emerged with Dalton. We will be using some of the laws that had been developed in Dalton's time to illustrate how the scientific method works. The concept of atoms dates back to the 5th century BC, when Leucippus and his student Democritus were the ones who first proposed that matter was composed of small indestructible particles. Democritus wrote that nothing exists except atoms and empty space. Everything else is opinion. He proposed that atoms exist in different shapes and sizes and move randomly through space. In fact, the term atom comes from the Greek word atomos, which means that which can't be split. Interestingly, the original idea for the indestructible particles from Democritus came when he was looking through a dusty room and noticed little dust particles that were floating through the air, and he credited that vision to his development of the concept of indestructible particles. Now, other major philosophers around that time, Plato and Aristotle, did not really embrace the concept of atoms. They held that matter had no smallest part, that it could itself be continuously subdivided into infinity. They proposed that the different substances were composed of various portions of fire, air, earth, and water. Interestingly enough, a lot of other cultures also developed this concept of fire, air, earth, and water. It wasn't just the Greek philosophers, Chinese philosophers, as well as a lot of different native tribes, such as those up in like Alaska, also developed this idea of fire, air, earth, and water, sometimes also including a fifth element, life. But because Plato and Aristotle were such big names in antiquity, their beliefs held a lot of sway, and this was actually the reason that the concept of atoms died out for almost 2,000 years, was because Plato and Aristotle viewed the four elements as being more correct. It wasn't until the late 1700s and early 1800s when an English chemist, John Dalton, conducting experiments on volumes and masses of gases, discovered a bunch of experimental results that were inconsistent with the elements that had been proposed by Plato and Aristotle. Instead, the results were consistent with this idea of indestructible particles that had been proposed by Leucippus and Democritus. And from this, Dalton developed the very first list of elements. Dalton's original list of elements can be seen here. These were the symbols that were used to represent the various symbols. So oxygen was a circle, hydrogen was a circle with a dot in it, and you can see from the various symbols, it would have been fairly cumbersome to use this shorthand representation. So for like mercury, you had this symbol, whereas barium was this. If we had used this in our modern method of writing out chemical formulas, it would actually be quite difficult to use. Now, some of the results that led Dalton to believe in the concept of an atom were related to the law of conservation of mass, law of definite proportions, and the law of multiple proportions. We will discuss these now and then indicate how those laws came together and are explained by the modern atomic theory. As a reminder, in the scientific method, laws are a summary of a large number of experimental observations. They do not explain why things happen. They are meant to be the what. So Antoine Lavoisier formulated the law of conservation of mass, which can be summarized as, in a chemical reaction, matter is neither created nor destroyed. So when a chemical reaction occurs, the total mass of the substance involved in the reaction does not change. The way that Lavoisier's experiments worked is he, as well as his wife, when they were working on it, had a sample that they would heat up, and then as the reaction took place, they would capture the gases in this jar. And Where his experiments differed from previous ones is a lot of the previous experiments on metal oxides that were done, they didn't bother trapping the gases. So when they weighed things before and after, there was actually a difference in weight. A lot of the earlier scientists, they didn't take gases into account. It was Lavoisier trapping the gases which really brought together the idea that the total mass before and after an experiment was the same. So this law itself is consistent with the idea that matter is composed of small indestructible particles, right? Because if matter can neither be created nor destroyed, then it has to be comprised of something that is indestructible. Then you had in 1797, the French chemist Joseph Proust reported on observations of the composition of compounds. By studying the ratio of metal oxides, metal carbonates, and metal sulfides, both naturally occurring and synthetic, found that the ratios of the metals to the oxygen, carbonate, or sulfides were the same whether the mineral was naturally occurring or created in the lab. So whether you made iron oxide in the lab or dug it out of the ground, or I guess the more common rust, Fe2O3, whether you get this from the ground, a rusting piece of steel, it doesn't matter. The ratio of iron to oxygen is the same whether it is naturally occurring or synthetic. Prior to this, a lot of people had thought that there was a difference between things that were produced in the lab, a synthetic mineral, versus a naturally occurring mineral. He summarized his observations as the law of definite proportions. All samples of a given compound, regardless of their source or how they were prepared, will have the same proportion of their constituent elements. Essentially, meaning no matter how you get Fe2O3, this particular type of iron oxide, whether it is naturally occurring or synthetic, it will be the exact same. Similarly, water, if you produce it through the combustion of hydrogen gas or dig it out of the ground or pump it out of the ground, it will be H2O. Whether it is naturally occurring or synthetic, the ratios of, in the case of water, hydrogen to oxygen will be the exact same no matter where the source is. This again is consistent with the idea of things combining together in indestructible atoms. This law of definite proportions is sometimes called the law of constant composition. Finally, you have the law of multiple proportions. It was in 1804 when John Dalton published his laws of multiple proportions, which essentially stated that when two elements, let's say A and B, form two different compounds, the masses of element B that combine with 1 gram of element A can be expressed as a ratio of small whole numbers. Essentially what this is meaning is that if A combines with 1B, you could also have a form of A combining with 2B or A combining with 3B. The key part here is that they are whole number ratios of their masses, right? So if the A to B ratio is 1 to 5, then this one would have a 1 to 10 ratio, and this would be a 1 to 15 ratio in terms of the masses. The key part here for the law of multiple proportions is you can have different combinations of your elements together, but they will always combine in whole number ratios. Now, Dalton's atomic theory explained all those different laws, right? The law of the conservation of mass, the law of definite proportions, and the law of multiple proportions. Again, a law is just a summary of observations. The theory is the explanation for why that happens. So Dalton's explanation for why the law of the conservation of mass and the other two work is that matter is comprised of tiny indestructible particles called atoms. Because they are tiny and indestructible, what you start out with needs to be what you end with. So that explains why you have the law of conservation of mass. Because they are indestructible particles, you can't get rid of them. And so whatever you start with is what you end with. All atoms of a given element have the same mass and other properties that distinguish them from atoms of other elements. So this again goes with the law of conservation of mass, as well as the law of constant composition and the law of multiple proportions. Because all atoms of a given element have the same mass, when they are combining together, you get those different ratios for the law of multiple proportions, which have the ratio of the mass of one thing to something else being consistent. And because they have the same properties, the law of constant composition would state that no matter where it comes from, the elements are all the same, whether it is a synthetically made compound from elements that you have in the lab or a naturally occurring compound using those same elements, the mass and other properties are going to be the same. Because atoms combine in simple whole number ratios to form compounds, this is consistent with the law of multiple proportions and the law of constant composition. Atoms of one element cannot change into atoms of another. In a chemical reaction, atoms change only the way that they are bound together with other atoms. Right, so the concept of the atomic theory, because your atoms are indestructible, because they combine in set ratios, this explains the perceived laws at the time. So the theory, again, is the explanation for the why. The laws are the summary of what.